We are now leaving behind the section of the course where we use statistics to organize and describe data. We're about to head into outer space, conceptual outer space, as we study the use of statistics for making inferences, and we need to understand some basics about how probabilities fit into what we're doing as we compare these sample means. So a definition. A sampling distribution is a frequency distribution of the values of a statistic when that statistic has been computed over and over, infinitely many times, with all samples of the same size. So here we have a population of scores. Let's create a sampling distribution. Well, sort of, not really, because we spend our whole lives doing it, but we can peek into the process of creating a sampling distribution of the mean using this population of scores. We will put these ages of inauguration into a hat and mix them up. We can draw out 3 scores, so n equals 3, compute the mean of those 3 scores, and throw them back in the hat. Draw out 3 more scores, compute the mean, and over with n equals 3 each time. And we will get lots of different means. The reason those means don't equal one another is sampling error. And if we keep drawing 3 scores, n equals 3, and we keep computing the means of those 3 scores, those means won't equal one another either because of sampling error. Also, those sample means, they won't equal their own population mean even. Because of what? That's right, sampling error. So here's a definition of sampling error. Sampling error is the reason we have a sampling distribution. The problem is that we are going to want to compare group means. Means for men and women on social support for some of you, from those who have versus don't have diabetes on COVID risk behaviors for others of you, and for still others, you might want to compare means from American Indians and Black Americans on sugar intake. And because of sampling error, we can't just look at 2 means and tell whether they differ. No 2 sample means look the same because sample means differ all over just by chance because of sampling error. But if we knew how variable group means were by chance, the men group means on social support and the women group means on social support, if we knew how much those means would vary just because of sampling error, then we can compare the men and women's means to one another and tell whether they were more different than would be expected because of sampling error. If the means were more different than what we would expect because of sampling error, we would call that a significant difference. But we are way ahead of ourselves. The bottom line is that the sampling error thing is important, and also it's important to know how variable these means are just by chance because of sampling error. Fortunately for us, we have a mathematical theorem that tells us how to calculate the extent of sampling error for a sample mean. The central limit theorem says that if you start with a population of raw scores, and those raw scores are finite, with a mean equal to mu, and a variance equal to sigma squared, and a standard deviation equal to sigma, then the sampling distribution of the mean, also known as the distribution of sample means, the distribution of sample means from those scores, all of the same n, that are sampled over and over and over and over, and the means computed over and over and over and over, the distribution of those sample means get more and more normal as n increases. And that sampling distribution of the mean will have its own mean, and we will call that mean of the sample means mu sub x bar. And mu sub x bar will be equal to the mu from the population of raw scores. Also, that sampling distribution of the mean will have its own variance, and we will call that variance sigma squared sub x bar. And that variance of the means will be n times less than the variance of the population of raw scores. And finally, that distribution of sample means will have its own standard error, sigma sub x bar. And it will be the square root of n times less than the standard deviation from the population of raw scores. And now we know how spread out those means are. They are the square root of n times less spread out than the raw scores. And the CLT, it really works. Our population mean was 55. Our sample means with n equal 3, the mean of those sample means was 54.97, and we only sampled 95 times. If we sampled infinitely many times, the mean would exactly equal 55. Our standard deviation of the means, the standard error of our n equal 3 sample means, was 3.8. And the standard error should be, according to the CLT, the standard deviation of the population of raw scores, sigma, and that was 6.52, divided by the square root of 3, the sample size. The CLT says our standard error of the mean should be 3.77, really close to what we obtained just for these 95 samples of 3.8. This process, it really works. And the variability of sample means, the standard error, gets smaller and smaller as n increases. So what's it all about? Statistics are estimates of parameters, inaccurate estimates of parameters. And even so, the sample mean is a good estimate of mu because the average of all the sample means, all the x bars in the sampling distribution of the mean, mu sub x bar, is exactly equal to mu. The central limit theorem tells us that. The central limit theorem also tells us how spread out those means will be in the sampling distribution of the mean just by chance when all the sample means are coming from the same mu. Because we know the spread of the means in the sampling distribution of the mean, we know the extent of sampling error. We can form an interval around our sample means and tell whether it's likely that another mean belongs to our group or is coming from another group with a different population mean. We also know from the central limit theorem that as the sample size increases, in our example it went from an n of 3 to an n of 20, that the standard error gets smaller and smaller and smaller. And the CLT, well, it's going to make all the difference in the world for what's coming up next, forming hypotheses and testing the null.